Okay, second method of integration, further method of integration I want to cover is integration by partial fractions. Before I do that, I'm going to spend this session actually revising the technique of resolving a function into partial fractions. So we're going to do that. There's further benefit in the fact that we'll be revisiting partial fractions again next year when we do electrical principles, because we'll need to do that for some of the work when we study Laplace transforms in electrical principles. So we'll need the algebraic technique again next year. I'll probably have to refresh it again then, but at least we'll have touched on it this year. I'm sure you all remember doing partial fractions with Mark last year. Maybe, or maybe not. No? Okay. At school, partial fractions? A levels? Okay. Anyway, we're going to do them now. So, by algebraic division. So, if I wanted to carry out that algebraic addition of two fractions, what do I need to do? Common denominator. Yep. So how do I get a common denominator out of that? What can I write there? What can I do to make it so I've got a common denominator for those two terms? If we wanted to do what would I do to find the common denominator? Multiply the denominators together. So 7 8s are 56. So my common denominator is 56. And then what do we have to do? Do to the top what you've done to the bottom. So to get from 7 to 56, I had to multiply 7 by 8. So I've got to multiply 3 by 8. It's 24. And then on this side, I multiplied by 7 to get to 56. So I've got to multiply 7 6s are 42. Now the denominator is the same. Can write it as one fraction, 24, 26, 66 over 56. Yep, and I also chop every fraction, but just an example. So the process is multiply the two denominators together, let's just separate them into separate fractions to start with. So we need, let's just start again. So our common denominator is x minus 2, x plus 1. And we got to plus that to x minus 2, x plus 1 on this side. Okay. So then what do we do on the top? yeah, to get this side, this fraction here, I've got to multiply the top by x plus 1. So that's simply 1 times x plus 1 on the top. Yep. And over this side, I had to multiply by x minus 2. So I've got to do 3 x minus 2 there. Yep. All get that. Now, what we can do then is some simplification. So, if I multiply out the bottom brackets, what do I get? X squared minus 2x plus x minus 2. Just multiply each term together. Okay, we'll simplify that again in a minute. And then up the top, I've got x plus 1 plus, and then we can multiply these brackets out, 3x minus 6. Yeah, all follow? And then bring together, in both parts, we can bring together like terms. So we got x and 3x's, 4x plus 1 and minus 6 is minus 5. That's the top line. We've got x squared as the only x squared there. Minus 2x plus an x is minus x. And then we got our minus 2 on the end. Hopefully I got that right. Everyone agree with that and see what that process is? Okay. What we want to do, partial fractions, is the reverse process of that. So we've gone from 2 partial fractions to 1 expression. The technique we want is the reverse process of that, going from an expression like this one to the 2 partial fractions we started with in the first place. So the reverse process of moving from that function, 4x minus 5 over x squared minus x minus 2, to these two, 1 over x minus 2 plus 3 over x minus 1, is called resolving into partial fractions. The first thing that we need to have is a denominator that will factorise, i.e. that we can put in 2 brackets. So this x squared minus x minus 2 will factorise to x minus 2, x plus 1. And the numerator must be at least 1 degree less than the denominator. In the example, 4x minus 5 has a degree, and that's the highest power of x of 1. And x squared minus x minus 2, the denominator, has a degree of 2 because the highest power of x is 2. Okay, so that are the conditions. So what we're doing today is that you must have a function like that to resolve it into partial fractions. If you don't have that, there are methods, but we aren't going to cover that. So we're not going to do any functions that don't have that condition. What we're going to look at this afternoon are 2 types of function that require resolving into partial fractions. Those involving linear factors, such as f of x is x plus a times x plus b times x plus c, resolved into 3 separate partial fractions. But those involving what's called repeated linear factors, where you've got something like a function of x over x plus a to a power. Okay? And that will resolve into 3 partial fractions like those on the board. So we're going to have a go at examples of both of those. Right, resolving a function with linear factors into partial fractions. So we'll go through the first one step by step. I'm going to write it out a little bigger on the board so we can see it all. We've got 11 minus 3x over x squared plus 2x minus 3. The first thing we've got to do is factorise the denominator. Okay, so that's a process of getting that factorised into two pairs of brackets. How do we do that? We know for a start off we're going to need x and x to get x squared. What's the process of finding the other two constants around? Yeah, what you're looking for is, first of all, two numbers that multiply to make up minus 3. I've got to multiply to make that. Multiply to make minus 3. And they've got to add to make 2. Yep. So what I generally do is over here I write down some of the options of two numbers that will multiply together to make minus 3. What have we got? 3 and minus 1 and minus 3 and plus 1. They have to be, because the answer is negative, they have to be of different signs. That's obvious. So either of those two options will multiply together to make minus 3, but which one will add together, which pair will add together to make 2? 3 and minus 1. So our 2 must be plus 3 and minus 1 in there. Yeah? And the top line has got to be this 11 minus 3x. So that's the first part, as to factorise the denominator. What we can then do is say that that is equivalent to, or is an identity of, equivalent to a over x plus 3, a being some constant, yeah, plus b over x minus 1. So we separate the denominator into two fractions. So we put an unknown, we put a constant on the top to represent the unknown numerators of each of those fractions. So if there was 3 terms under here, we'd have 3 constants on the top, and so on. We certainly won't be doing any more than 3 factors. Right? All following so far? Next step is to make the right hand side have common denominator. So we want, on this side, we want this 11 minus 3x over x plus 3 x minus 1. We want to return that common denominator to this side. So, if we look at that in terms of that, what have we got to multiply by to make that denominator x plus 2, x plus 3 times x minus 1? We've got to multiply by x minus 1. So we'd have to also multiply a by x minus 1. So we end up with, at the top here, a x minus 1. Plus, over this side, to get this to the common denominator we're looking for, we'd have to multiply by x minus 3. So we end up with b x plus 3 on that side. Yep, everybody follow that. So now we've got effectively got our two partial fractions with common denominators. Yep. What we do now is we say, because of the left-hand side and the right-hand side are equal, then numerators are also equal. And I'm going to put it in a different colour. This is called equating the numerators. So if you were writing out the method, you'd just go now equate numerators, rather than all that stuff in green. It has to be true if these two, there and there, the two denominators are equal, then the two numerators must also be equal. So what we can say here then, what we're saying is that 11 minus 3x is equal to a x minus 1 plus b x plus 3. Yep. All okay? Yeah. Anyone remember how we can eliminate one of the variables on the right hand side, either a or b? No? What happens if I let x equal 1? A will be a, but then a x minus 1. That term becomes 0. Yep. By letting x equal 1. And we can then go, therefore, 11 minus 3 times 1 is equal to b brackets 1 plus 3. And to start with, that's useful to write all these things out longhand until you get used to it. So this is 11 minus 3 is 8, is equal to 4b. Therefore, b is equal to 2. Get that? So along that lines, what do we now need to do to find a? Yep. So we've done that. So we're now making this term equal to 0. Yeah. And therefore, 11 minus 3 times minus 3 is equal to I times minus 3 minus 1. 3 times minus 3, minus 9. 11 minus minus 9 is 20. It's equal to a minus 3 minus 1, a times minus 4. Therefore, a equals 20 over minus 4 minus 5. Agreed? Yeah. Lastly, put constants A and B back into partial fractions. So our partial fractions were separately I over x plus 3, b over x minus 1. So I was, we're saying now, 11 minus, we're saying this bit, 11 minus 3x over x plus 3 x minus 1 is equal to b is positive, so we'll put that one first. B was 2 over x minus 1 minus 5 over x plus 3. So we resolved that into those two partial fractions. Well, that one's a bit more long-winded because I did quite a bit of writing about what the next step was that you wouldn't have to do. You'd just simply say therefore, and you'd say equating numerators. You wouldn't write everything that I've written every time. Just the first example. Yeah. So that's a process, and that's a process we're going to use next week. For instance, we can't integrate that, but we can integrate those two separately using what technique? Sorry? What were you doing this morning? Algebraic substitution. Yeah, let these bottom terms equal u, so we can do those two separately, can't we? Because we can do we know we can do the integral of that term, take away the integral of that term, and we can do each of those two terms by algebraic substitution. Yeah. So, this example, one where there are 3 terms on the bottom, and I'm not giving you the multiplied out term to factorise into 3 terms, it's just giving you like that with the terms already as factors. So, in this case, we've got 2x squared minus 9x minus 35 over x plus 1, x minus 2, x plus 3. Yeah, we can say that's equivalent to I over x plus 1 plus b over x minus 2 plus c over x plus 3. So it's got 3 terms, we need 3 constants. So what's the next step? Got to multiply them, we've got to put them over, go on Jack, sorry. Denominator common again, yeah? So we want this common denominator, x plus 1, x minus 2, x plus 3. Yeah? So what we got to do to a, in terms of the numerator then? I'm probably going to have to take that out of there so I can fit all this in. Let's make it a bit smaller. What have I had to multiply? What we've got to do here is look at what I've had to multiply x plus 1 by to get to this common denominator. Yeah? B, I've had to multiply by x plus 1 and x plus 3, and C, still running out of space. by x plus 1 x minus 2. Yep, bit messy, I know. Alright, but what do we do next? What's the term called? Equate numerators. So we say 2x squared minus 9x minus 35 is equal to a x minus 2 x plus 3 plus b x plus 1 x plus 3 plus c x plus 1 x minus 2. Yep. Is there something we can do that will eliminate two of those variables? What could we do so that we can eliminate B and C and effectively find A? Remember that these three things are multiplied together, those three things are multiplied together. No, you don't need to do that. What you're looking for is a term, right, that's in both that bit and that bit, a term that's in both of them, x plus 1. Now, what can we do to make those two terms disappear, knowing that x plus 1 is in both of them? If you make x minus 1, that term will be nothing, and that term will be nothing. If that term's nothing, then b times nothing times that is nothing, and c times nothing times that is nothing. So by making x minus 1, because that bracketed term is in both of them, we eliminate both of those parts. So we let x equal minus 1. Therefore, 2 times minus 1 squared minus 9 times minus 1 minus 35 is equal to a times minus 1 minus 2 times minus 1 plus 3. Calculate if you need to. What does that bit evaluate to? Minus 1 squared is 1. That bit's 2. Minus 9 times minus 1 is 9. So that's 2 plus 9 minus 35. Did you put that minus 1 in brackets and then square it? It's equal to minus 1 minus 2 is a times minus 3 times 2. Minus 24 equals minus 6a. A is equal to 4, is it not? Yep. Okay. So we now know that A is equal to 4. What's the next thing we can do to eliminate terms? Yeah? If we let x equal minus 3, we end up with 2 times minus 3 squared minus 9 times minus 3 minus 35 equals. And then that side, A term's gone, B term's gone, we get C minus 3 plus 1 times minus 3 minus 2. Yeah? Wait, that's minus 1. We let x equal minus 1. That's this board. That's not always right in the right place. But you're right to point it out, Aaron. Thank you. All right? You're happy now? Minus 1 plus 3 is 2, yeah? All right, what does this bit equate to? That bit's 18. That's bit 27. Am I right? What did that equal altogether? Sorry? 10. And this side? Ten is equal to 10c, therefore c is equal to 1. Lastly, what do we need to do? Eliminate both the a and the c terms. That x equal 2, isn't it? So we've got 2 times 2 squared minus 9 times 2 minus 35 is equal to, and we're looking at the b term now, b brackets 2 plus 1 brackets 2 plus 3. Minus 45 is equal to 15, isn't it? 15b. minus 3, that's 5. 3 5 is 15. Yep. Therefore, b is equal to minus 3. So all that's left to do is to put them all back in. X squared minus 9x minus 35 over is equal to 4 over x plus 1 minus 3 over x minus 2 plus 1 over x plus 3. These three came from your constants, so that one was b. The one there is C, and that one is A. Yep. Bit messy, but if you're careful, push the right buttons on your calculator when you get towards the end, you should get the right answer. Right. Right. Dissolving functions with repeated linear fractions into partial fractions. So this is the second type that I highlighted earlier. 2x plus 3 over x minus 2 all squared. That type is equivalent to I over x minus 2 plus b over x minus 2 squared. Because the denominator contains a repeated linear factor, i.e. a bracketed term raised to a power. The process is somewhat similar though. We can put that as equal to, and the first thing we want to do is return to our common denominator of x minus 2 all squared. What would we have had to done to this fraction to make that x minus 2 all squared on the bottom? Multiplied by to make that x minus 2 squared on the bottom, we've got to multiply that by x minus 2, haven't we? Yep. And then what have we had to do to get that to x minus 2 squared? We haven't done anything. So that's just b. And we've got to confirm that this is that side is equal to that. or equivalent of that. What do we do next, do you think? What did we do before? Equate numerators. What term can we get rid of and how? Someone dying out there. Let x equal what, Catherine? 2. Let x equal 2. Done that right? Yep. Seven? Now what do we do? We can't get the b term equal to nothing, but what can we do? Take what away? Yeah, that'd be handy, but that won't work, I'm afraid. So, yeah, what substitute 7 in for b. So we got 2x plus 3 is equal to I x minus 2 plus 7. Is that right? What? Substitute it into what do you mean keep x equals to 2? What else could we let x equal? That won't affect b. What's everybody's friend for x? Yeah. So we get nothing plus 3 I equals 2. Follow? Hence, our original thing here, copy, just put our I and B back in, do that. So that's I x minus 2 plus B. A was B was 7 over hang on, I want separate, don't I? I'm going to put it in that. I over x minus 2 plus b over x minus 2 squared. Sorry? Took 7 from both sides. Yeah. Yep. All done. Easy peasy. Lemon squeezy. Start having a go at that one. Got a cube term on the bottom. Cubed. So that's going to be equivalent to I over x plus 3 plus b over x plus 3 squared plus c over x plus 3 cubed. The next bit's going to be pretty long because there's a repeating linear factor underneath. So term raised to a power. Well, right up front, so we were going to look at two different types of partial fraction. Those involving linear factors, different linear factors. And then this one is the same linear factor raised to a power, so it's the same thing repeating. So that's I over the three different factors. This is I over the factor on its own, over the factor squared, over the factor cubed, and then if you add to the power 4 or 5, you'd carry on. Does that make sense or not? Because, well, you could do it that way, but I think this simplifies it a little bit. Because when you're now looking to make the denominator equal to x plus 3 cubed again, aren't you? Yeah. So what have you had to do to A What have you had to do to the denominator here to make it cubed? Multiply by x plus 3 squared. Yeah? What have you had to do to that to make it x plus 3 squared? Multiplied by x plus 3. What have you had to do to c? Nothing. Yeah? I see, said the blind man. And then what do? Equate the numerators. Three x squared plus 16x plus 15 is equal to I x plus 3 cubed plus b x plus 3 squared plus c. Have I got that right? Have I gone wrong somewhere? Oh, hang on. Yeah, I'll put one too many. You're good at spotting my deliberate mistakes, aren't you? Right, equating numerators. What can we do now? Get rid of two terms. Yeah. X equal minus 3 will eliminate these two. Where? Not a deliberate mistake you spotted, Kieran. Minus 3 squared is 9, and times 3 is 27, that bit. Minus 48 plus 15 equals C. C equals minus 6 What can we do now? It's a bit more tricky now. Anyone got any ideas what could be done? And to what end? Any ideas? What you have to do, if we call this identity 1, that one there, yeah, we need to expand that. We need to get rid of the brackets in that right hand side. So we have to go 3x squared plus 16x plus 15 is equal to a times, and what's that x plus 3 squared term multiplied out? X squared plus 6x plus 9. Yep. Plus b x plus 3. Right? Happy? Now we multiply out those brackets. Yep. Well spotted, that man. For the moment we'll put it on the end as plus c. Yeah, I know we know what it is, but let's put it on as plus c on the end for a minute. Now what we can do is we can equate particular terms of x. We've got on this side 3x squareds, and on that side how many x squareds have we got? Ix squareds. Yeah? So we can go equate x squared terms. 3x squared yep. Therefore I equals 3. And then we've got 16x's there, And what x terms have we got on this side? 6x and bx. So equating x terms, I've gone wrong somewhere. Have I missed an x term somewhere? I've taken 6x from both sides. I make 10x that side, don't I? We got this repeating linear factors, so we write it out 3 constants. The first one of the x plus 3 term, b is over x plus 3 squared, c over x plus 3 cubed. We do the same process as we've always done before to get back to our common denominator. Go ahead and equate numerators like we've always done. These 2 terms are relatively easy to get rid of by making x equal to minus 3, and we find c. Then if things get a little bit more tricky, you need to expand the terms in the original identity, and then we can equate the x squared terms and equate the x terms to find the constants a and b, giving our final answer like so. And on the following page of your notes, in good old-fashioned style, there are some examples for you guys to have a go at. So practice makes perfect.